The recording is started, so we can start. Just give me 1 moment. Okay, we already have some questions, so that's good. Okay, so let's just start from the very beginning of the assignment. So let me just repeat what I said a little bit earlier, is that so after today, I want you to be able to submit the assignment by the end of this week. That is before Friday, by the end of Friday, okay? And okay, let me share the screen. All right. Okay. Now, since this is formally a lecture, so let me add a new. All right. Okay, so the first question, so Captain Hook, I'm going to come back to your question in a few minutes, but I think let's just start with the beginning. So did you guys have questions about problem 1?
Yes, I did.
Okay, so can I just like explain the setup for problem 1 so the question can be a bit better understood by everyone?
That's actually my problem. I didn't understand the
that's fine.
constraints.
So the idea is that we have 2 thermally insulated cylinders. That means that there's no heat going in and out, right? So any process that involves these 2 cylinders, they will be necessarily adiabatic, right? Because there's no heat coming in or out. And I think there is actually some ambiguity, but let me just get to the. So this is cylinder A, and this is cylinder A, and this is cylinder B. And there is some piston, and initially the cylinder A has the piston here. So this is the piston. Sorry, this is not a very convincing piston, but you know what I mean. Here's another piston, and for the time being, so this, and there's a stop here, okay? And there's a gas in chamber A, and there's nothing in chamber B because the piston is all the way depressed, right? And we're just gonna ignore the gas in the little, valve, connecting valve. Okay, so this is the setup, and then what happens is that this guy has some is at some volume. So this is volume V, and this is also volume V, and this thing has some temperature T. Okay, and this is a monatomic gas. So it's a monatomic ideal gas. I mean, it doesn't say so, but let's assume it's an ideal gas. Okay, so then there are 2 scenarios scenario number one is that the valve is opened and the gas is drawn into B is slowly drawn into B by pulling out piston B. Okay, so that means that we take this setup and what we do is that we slowly pull out this piston until it's fully pulled out here. Okay. So, and the valve is open, so the valve is, we can no longer there. And so what will happen is that this, gas will expand into this, region B as well. And the problem is to find what the temperature of this gas is. So, this is no longer going to be, this is no longer going to be at temperature T necessarily, right? So the idea is, after this happens, there is some final temperature, T of F, Now the question is, what is T of F, okay? That is question number one. And setup number two is that piston B is fully withdrawn. So here, this piston is being slowly withdrawn until it is, right, yeah. So, yeah, it's, but in the second one, what happens is that, first you withdraw the piston, but the valve stays. So the second one is something like, let me try to draw this, is you keep the valve as it is, but you withdraw it until the piston is here. And then what you do is then you slightly open it. So the valve is still there, but there's a small opening. So if there's a small opening, the gas is not escaping to this region very quickly. And then what you do is that you push this valve, this piston in, slowly, such that the pressure in this chamber, remains constant, okay? So at the end of, and you do it as far as this, piston goes in, right? That's the idea. So at the end of the exercise, what you'll get is you will basically get the piston over here. And because these two guys have the same volume, the gas will basically now be over here, right? It doesn't say that. It just says that you are pushing the piston as much as it can go in. But from the fact that, this situation and this situation is symmetric, you know that this is also physically realizable. Okay, so those are the two setups, okay? And now you have to calculate in both cases what the final temperature is going to be. And in this case, yeah. Okay. So in this case, the final temperature here is going to be the final temperature here, right? Okay, so that's my understanding of the whole thing. So now, any questions, Saif? Is that clear now?
Yeah, mostly I'm just thinking about like what it's such an unrealistic kind of situation that I'm not sure exactly what the constraints will be due to this kind of operation.
So the constraint is that it's thermally insulated, and that's actually pretty easy to do in experiments. And so the constraint is that it's thermally insulated. If the processes involved are quick enough compared to the rate at which heat is absorbed by the system or given up, then you can do a pretty good approximation of an adiabatic process. And in both of these cases, the idea is that it's adiabatic. And if you go back to some of the lectures or look at Blundell, you will see that for adiabatic expansion, which is the first case, and also the second case, you could say, there are some for adiabatic expansion of say monatomic ideal gas. There is a very particular equation, right? So we know that the temperature and the volume raised to gamma minus 1, where gamma is Cp divided by Cv. And this has a very particular value for monatomic gases.
So 5/3.
Yeah, exactly. So this is 5/3, right? So this thing remains constant when you have an adiabatic expansion, right? So that tells you everything you need to know to find out what the temperature is going to be, at the end of this process, right? So I think that's a good hint. But the second case is that there's actually if you look at the first chamber, what you're seeing is that you are seeing again, we use the fact that we are using an ideal gas. And for ideal gases, the U is just a function of T, and therefore, change of the internal energy is like this is an expression we have for ideal gases. It's not true for gases in general, but this is true for ideal gases, right? So now the thing is that because we have an adiabatic process, that means that d of q is 0, right? So then what we can say is that, okay, we have the first law, which is, say, d of u equal to, say, dq, and then minus, say, p dv, right? And what we have here is that this term drops out, and du can be written as cv of dt, and then we have minus p dv, right? So, we know for ideal gases what P is. PV is equal to, if you have n moles, nRT divided by V, right? So now we can plug this into this equation, and then the rest is very easy to do, right?
So is this for 1.1?
This is 1.2, right?
Yeah, this is 1.2.
Yeah, this is 1.2. Okay, so this is basically problem number 1, okay? Okay, any more questions from here?
So for 1.1, the temperature wouldn't be the same, right?
Well, I mean, this thing, I mean, you tell me. I mean, this thing remains constant. V is changing. So would T be the same?
No.
Yeah. So it wouldn't, right? So
In 1.2, is it correct to assume that dV equals 0 since the initial and final volume are the same?
um, is it correct to say? Let me just think about it 1 second. So I think a better way to look at it is to just look at the gas in chamber A.
I think the reason I'm confused is because I'm considering both chambers at the same time.
Yeah, I think that's where I also went wrong the first time I did it. But if you read the question again, it's just saying that all you're doing is keeping the pressure constant in chamber A. And you see that chamber B, the pressure is not being constant, right? Because chamber B you've already extended, pulled out the piston as far as it would go, right? You have done this. So let me use a different color. So you have already pulled the piston as far as it's possible. And then what's happening is that as gas is filling in, the pressure in chamber B is going up, right? And therefore, you can't really use the fact that P is constant anymore, and or even P. Sorry, that's what it's saying, right? Yeah. So, which is something you should probably use for for chamber A, right? You see what I mean? In fact, as I said before, you don't even have to use this if you assume that P is constant, right? Because P is constant, so you just do the integration.
Yeah, I mean, the limit of integration on the B side I was thinking about.
Yeah, it goes from V to 0, right? Yeah, so you actually, if you constant on chamber A, then you don't even have to use this. Then all you need is just you just use the fact that P is constant, right? Okay. So let's move. Yeah, let's move on to the next one. Unless okay, Zabir is here, so let me make sure you are.
So I'm having trouble with my internet today, so sorry about
It's okay. Yeah. So I'm just going to. It's going to be like recorded, and I'll put it because there's not much to edit. I'll just put it up right after the class. So, all right. So next, let's move on to say problem 2. Oh, problem 2. Sorry, I'm not gonna do any problem 2 because problem 2 is essentially you like either thinking about it or looking up the answer and explaining it in your words. So one thing I want to say about problem 2 is that I want figures. I want figures explaining your answer. Number 2 is the number 1. Number 2, I want you to explain in your own words, right? the the answer or the setup. Okay. Now, if you copy from another person, what will happen? Tell me.
Sentences will be identical.
Yeah, exactly. Words will be identical, right? You can have somebody explain it to you like, oh, I'm not really understanding this. Can you help me? And you can say, sure, somebody can help you. And there's nothing wrong with, a friend, helping you figure out the answer, or help you figure out the answer, or figure out, give you understanding. But once you've understood that, you need to take a minute and just trust yourself and write it out yourself. That's how you learn to do things, right? You actually have to trust yourself, and there is no better place to learn physics than in trying to solve problems. It took me quite a while to solve these problems. I mean, when I assign problems, I don't think whether they're easy or not. I just don't know what the solutions are. I usually just assign them because I think they're interesting. And then I go and I have to, figure them out myself. And sometimes it takes me a while. So, maybe, you guys should trust yourself and try, okay? Okay, so that's problem number 2, that use your own words and your own figures and try to understand, okay? Now, problem number 3 is non-trivial, I think, but let's move on. So all I'm going to say about problem number 2 is that to show that, Clausius's law leads to Kelvin's law for formulation of second law is to prove that if you violate Clausius's law, then you should be able to show that you're also violating Kelvin's law.
Sir, I had a confusion. So
Yeah.
it's kind of, we're taking a contrapositive way of proving it, right?
Yeah.
So we should first take a Kelvin violator, right? Because you see, like in the question, we're asked that we have to prove Clausius to Kelvin. So it's essential to prove not Kelvin to not Clausius instead of not Clausius to not Kelvin. But the hint says otherwise.
So in class, what did I do? I showed that if Kelvin doesn't work, then Clausius doesn't work, right?
Yes.
If you have a machine that violates Kelvin's law, then it should also violate Clausius's law. Yeah, I think you may be right that there is some logical inaccuracy in the wording, but what I want you to show is that if you violate Clausius, then you are violating Kelvin.
Sir, I have a little question about this. Sir,
Yeah.
as we have already covered in our class that Kelvin's statement violates the Clausius' statement, so do we have to refer to those that procedure to answer this question?
No. This is completely independent.
Okay, sir.
Yeah, this is completely independent of that. Yeah.
Okay, sir.
In fact, it's a different setup that you have to consider. Okay. And I mean, try it yourself. If you can't figure it out, look it up. The solution is there. Everybody knows about it. But then understand it and explain it yourself. The better the explanation, the more marks you're going to get. I don't want you to kind of just like, I don't want a monosyllabic or one-line explanation. I want you to go into the guts of it and try to, I want to see you thinking, right? Okay, so, okay. Right, okay. Zabir Hussein. I already gave Zabir, okay. Let me just do another. Is Mehtab here?
Yes, sir.
Okay, good. And Afia, are you here? Okay, Afia is not here.
Sir, I joined a little bit late.
Nafiz, yeah, I saw that.
So Nahi, me too.
Yeah, I also saw that. Okay. Sitima, are you there?
Yes, sir. I'm here.
Okay. Oishik Hassan?
Present, sir.
Okay. Oh, very good. Okay.
Sir,
All
Muhammad
right.
Abdullah.
Yeah, I already got you. Yeah. All right, so let's move on to problem number 3. And problem number 3 is saying that you have some sort of cycle, which is not the usual cycle. And the cycle looks something like this, that it's on a PV diagram. So you've got an ideal gas, right? So this is P, and this is V. And you start with some value of the pressure at P1 and some value of the volume V1. So this is the point you start with. And then you quote unquote cool the gas. That is, and the volume goes down to V2. But the pressure remains the same, okay? So this we can call phase 1. And then the gas is heated to constant volume, so V2 remains the same. But since the gas is being heated, its pressure goes up, and it goes up to the pressure, say, P2. Okay? So it's an isochoric, I think, expansion. And then the gas is adiabatically cooled. So that's not an adiabat.
So wouldn't it be isobaric?
Isobaric was phase 1, right? Because the pressure was constant. Bar is pressure.
Oh yeah, okay.
Yeah, the second one would be isochoric or something. Just like some Greek name or Latin name that we don't care about. Okay, so let me just erase some of that. Okay, and so this is phase number 2, and this is phase number 3. Okay, and so the temperature here, say, was T1, and the temperature here was, say, T2, and the temperature here was T3. So this is a cycle, right? It's a cycle of an ideal gas. So suppose that you make a machine or an engine which, instead of doing a Carnot cycle, does this cycle. Then what they want you to prove is that they want you to prove that the efficiency of this machine is given by 1 minus gamma, and then V1 by V2 minus 1 in the numerator, and then P2 by P1 minus 1 in the denominator. Okay, so this is the, so how would one approach it? Did anyone solve it yet?
I tried.
I think I did. I could show it.
Yes, sir, I solved it.
Yeah.
Oh, very good. Okay.
I did it, but I had a minus sign which I had to kind of get rid of using an argument, which I'm not sure about.
Okay, well, I'm sure then if it must be a good argument then, because yeah. Okay, so of course, I'm not going to give you the solution, but I'm just going to give you some hints. Okay. But first, are there any questions that I can explain about the
Yes,
setup?
sir.
Yes, please.
In process 2,
Yeah.
if I write QH, so it says QH, heat entered the system. So
Exactly.
QH would be CV dt. Now this dt is T2 minus T3 or T3 minus T2?
It should be T3 minus T2, right? Because it's a positive quantity. Because okay, yeah, that's a good idea, a good question. So you're saying that you're looking at the heat that entered at this phase, right? And you're calling them QH. I'm calling it delta Q23. So it doesn't matter what you want to call it. And here it's cooling down, so heat is going out. So that is delta Q12, say. And you're asking whether or not one should have delta Q23 equal to CV times T2 minus T3 or T3 minus T2, right? Now see that delta Q23 is a positive quantity. This is a positive quantity in general, unless you're dealing with black holes or something. And then this should be then, since you're heating it, so T3 would be greater than T1, right? Okay?
T2?
So T2, you're right. Okay?
Sir, I have a little question here. So from process one, basically from T1 to T2, can we say that as the temperature is, as the volume is decreasing, and our pressure is constant? So as we know from the equation PV equals to RT, our volume is directly proportional to temperature. So T2 is actually lower than T1, right?
Yeah, exactly. T2 is lower than.
So can we say actually that heat is going into the system? That means
No,
if we talk about this is the energy.
So in the phase one, heat is actually being given up by the gas, right? So delta Q12 would be proportional to, say, T2 minus T1, which is a negative quantity. And what would be the constant of proportionality here?
Heat capacity.
Which heat capacity should it be?
The pressure on CP.
Oh, that is CP.
CP, exactly.
Or
because
CP.
Your pressure is being kept constant here, right?
Pressure is constant.
Yeah. And then, you can see now how it's going to play out. The way it's going to play out is that at the, like nothing exciting happens here because there's no, heat is being exchanged with the system, with the environment.
Sir,
So,
I had a confusion. Like in delta Q23, so it's like CV delta T. But I was thinking in terms of the first law of thermodynamics, work is still being done, right? From like 1 to 2. Like isn't work being done?
Exactly, it is being done, yes.
Oh, and is that why we have the CP here?
Exactly, otherwise you'd have CV.
Yeah. Okay.
Yeah, otherwise you'd have CV here. Yeah, that's a very good question.
Yes.
Yeah. Okay. So now we know that, after a cycle, we are back into the same point, right? Therefore, the total internal energy change in internal energy must be 0. So that means that the work done in going around the cycle must be equal to the total heat exchanged. Now, which we know is simply delta Q12 plus delta Q23. And then the efficiency is going to be W by the heat that you absorb. So that'll be delta Q23. And when you plug these in, these expressions now. When you plug this in, you get a t-dependent function of, say, T1, T2, and T3, where you have you have the ratios of these T's. But then you're dealing with an ideal gas. That means that P1 V1 must be equal to nRT1. Then P1 V2 must be equal to nRT2, and then P2 V2 must be equal to nRT3. So you can take various ratios and get rid of the T's here, and you should be able to get the correct expression for eta. Okay. So
I see where my minus sign came from, but instead of like saying that it's equal to 0 and then taking it to the other side, I just said that since it's heat that's flowing out, I have to add another minus sign in order for it to become
right. So yeah,
an
you're
absolute.
correct as well. Yeah. Yeah. So you did take that into account. You just did not like take into account automatically. You put it in by hand.
Yeah, I did it more like a physical argument than a
Yeah,
mathematical.
your definition of heat is always positive.
Sir, I was wondering, like, for the notations you use, they would become much more useful for multi-step processes, right? Like when we have to deal with multiple steps.
Yeah, exactly.
Oh.
Sir, would this work if eta is equal to 1 minus QC by QH?
No, eta is not QC by.
1 minus QC by QH. That's what I
Or
tried.
Q out by Q in.
So this is what you're calling QC, and this is what you're calling QH, right? And so QC plus QH divided by QH, right? So that is, so then this would be 1 plus QC by QH. Yeah. So this is, this is, you don't. So what what I think you're doing here is that you're taking both of these things. So sorry, you're saying that this is QC. The first thing is QC, and the second thing is minus QH. No,
So
you're saying this is plus QC. This is minus QC.
For phase 1, I took QC, and for phase 2, I took QH.
Yeah, but you're saying QC is the positive amount of heat that is being given up by the system. In my notation, that is equal to minus of this.
Yes, so basically I was
And
thinking
then
that when the heat is given heat is given out, I was taking minus
and
as
there's a minus
exothermal.
sign, yeah, there would be a minus sign here according to your definition, right? But in my definition, delta Q is equal to minus QC. So according to your definition, there would be a minus sign here. Okay.
So I guess it pays to have the definition stated in the question, like which one we're using.
Yeah, it's a minor point. And is somebody shooting in the background?
Yeah, there's a construction.
I'm like, what is happening? Are you coming from a war zone?
So he lives in Iraq.
Okay, let's not get into that. Either Iraq or I don't know, Mirpur, right? So sorry, Mirpur just looks like a war zone whenever I go there. So I'll edit. So if there are people at Mirpur, I'm very sorry. That was a joke.
Sir, I am from Mirpur, but I agree with you. Also, it's an ocean. It's an ocean here.
It's a construction. All the construction, right? It's just all the construction makes life very difficult. Yeah. All right. So, Afia, you're here. Good. Afia, would you mind staying around after the class for a few minutes? I wanted to have a chat, if it's okay. Otherwise, we can talk later.
All right. Yeah, it's okay.
Yeah. Okay. All right. So, I think that deals with the problem number 3. And so let's move on to problem number 4. Did people do problem number 4?
Yes, sir.
Yes, sir.
That's probably one of the easiest problems, right?
Yes, sir. The answer is in the question.
Yes.
Yes, sir. Question number 4 is one of the easiest ones.
Yeah. Okay. Then I'm gonna skip over 4 if you guys don't mind, unless somebody wants me to like give you some hints. The biggest hint I can do there is that convert centigrade to Kelvin. Okay, so I forgot to do that the first time I did it, and I didn't get the right answer.
Okay, isn't that kind of obvious in thermodynamics?
So does it even matter actually? Because as we're calculating delta, So minus 273 and plus 273 in calculating TLT, the conversion
Wait,
of
yeah, it does
Celsius to
matter
Kelvin
because
actually
when
cancels out.
if you're doing log TF by TI,
It will affect the integration as well.
it'll affect, you know, the
Dalton
ratio is
bonus.
different, right? It does matter.
Yeah, I got it wrong the first time because of this.
Yeah, exactly. So it does matter.
Oh, so okay.
Okay. So yeah, there's something actually very useful and deep about the Kelvin temperature scale.
So hypothetically speaking, is it even possible to actually reach the 0 Kelvin? I don't think so, right? Because
Well,
things start to
that's
get
a
very
third
weird
law
at
of
that temperature.
thermodynamics, right? No, the fourth law. The fourth law is saying that you can't reach the Kelvin scale because, you know, because
It would require infinite
yeah,
steps.
you know, we saw that, like, you know, it was a very heuristic argument, but you know, it requires an infinite number of steps. Okay, so let's move on to problem number 5 then. Oh, this is going to be a short class. Problem number 5 is similar to problem number 4, but the first part is exactly the same thing as 4, right?
Yeah, I got stuck on this because I didn't realize that the math and its contents, heat capacity, was like applicable to the entire question because it looks like it's only for number 3.
Sorry, what do you mean?
In Blundell, the last sentence is given separately at the end, whereas like the last sentence in the as it's written in the question paper looks like it's part of number 3. So I assume that.
Oh, the math and its constants have total heat
Yeah.
energy capacity. Oh yeah, I'm sorry about that. That's my fault. Or I should have proofread the question more closely. Thanks for pointing that out.
For 1 and 2, I just kept the C.
Yeah, you can also do
that
that.
C.
Yeah, you can also do that. And you know, the thing that I worked out, I actually kept that as well, CV. So yeah, I actually didn't notice that CV, the value of CV was given. So all my answers are in CV. So it's good that you pointed it out. Thank you. So okay, the first part of problem number 5 is the same as before, right? And but the problem number 2 is easier than problem number 1 because in that case the temperature is remaining constant. So do you want me to give you some hints about problem number the second part of problem 5?
Yes, sir. A hint would be helpful.
Okay, so so from problem number 1, we know that how much heat is transferred from the reservoir to the bath, right? So this is basically just CV times TF minus TI, right? And so that's the heat. And then the change in entropy for the heat reservoir would be that the heat that it gives up. So the heat it's giving up is, if it could be the negative of that, right? It could be minus CV TF minus TI. So this is basically delta Q. And its temperature remains constant. It is the final temperature, right? So usually, you know, usually what we have is that delta D of S is dq by t, and then we calculate a finite change in entropy by doing this, right? From the initial state to the final state. Usually it's usually t is a function. It's not a constant. But in this case, it's a constant, and therefore we can factor it up. So it's even easier than the previous one, because in the previous one, in section 1 of this problem, you actually have to do this integration, right? Okay.
Yes, sir.
That's the thing. Now, I suppose that, what about the third problem, the third section of this problem?
I had a big question about this one,
Okay.
which is that, like, I calculated the efficiency of the Carnot engine with the two reservoirs temperatures, but I was thinking that I'm using the efficiency in the problem, but as the temperature of the cold reservoir gets to the temperature of the hot reservoir, shouldn't the efficiency keep shrinking? But I'm assuming that it's constant in order for the math to work.
Yeah, that's an approximation you have to actually make, and I guess the idea here is that in a real Carnot engine, this would not be done in one cycle, but here it's probably going to be done in one cycle.
What's the significance of one cycle?
Well, if it's done in one cycle, then then the temperature just like jumps.
Ah, okay.
Right. I mean, I think there is subtleties that one is actually shoving under the carpet there. I am not going to deny that.
Sir, can 3 be done using QC by TC is equal to QH by TH?
Yes.
Do we have to prove that or anything?
No, you don't have to prove that. So, anyone else who wants more, like, I think we're talking about the detail, but would anyone else have questions, say, about the whole setup? Is everyone fine with the setup of section of problem 3?
Problem 3.
No, sorry, not problem 3.
5.3.
Yeah,
Pachet
5.3.
3.
Yeah. Pachet 3. Thinner part. No, Pachet 3. It's like Lalmati address.
Sir, isn't it basically calculating the total entropy of the whole system, reservoir and the surroundings?
5.3 is, there's a Carnot engine, right? So let me just like show you the setup, and then you can and give you a couple of hints, okay? Because I feel that maybe some of you are feeling shy or something, and so I'm just not getting a very strong, yes, sir, we have no problem with this, move on vibe.
5.3 is definitely pretty
Yes, sir, we have
complicated
no
situation.
problem.
You have no problem? No
sir.
one else has problem, because then I will move on.
Sir, I have problem. I have
Okay,
to
good.
understand.
Okay, then I will not move on. Good. So the setup is something like this, that you have a reservoir. The reservoir is at some temperature, T final or TH, okay? So which we call TH when we are doing Carnot. And then you're drawing heat from the reservoir, and this is going to be Q of H. And then there's a Carnot engine, which is this magic circle. Okay, Carnot. And then what we're doing is that Carnot engines, what they do is that they take heat from a hot reservoir, and then they convert some of it to work, and then they dump that heat, not that heat, but part of that heat, into a colder reservoir, which is say QC, and that colder reservoir, we are going to take that as TI, or the bath, the initial temperature of the bath, which we are calling TC. Okay, so this is the setup, and the thing is that what we do know is that we know what QC must be, right? Because we calculated QC here. This is the energy, the heat that has to be dumped in the cold bath so that its temperature goes up from TI to or T final, right? So we know what QC is. We also know what TC is, and we also know what TH is. If I'm given the TC and the TH, I can calculate the eta, the efficiency. Okay, and there's also another expression for the efficiency, which we just used a minute ago, which has to do with QH plus or minus QC divided by QH, right? So you know what the efficiency is, you know what Q of C is, so you can find out what Q of H is, that is what this heat is. What is the amount of heat that is being given up by the reservoir? And once you know what QH is, you can work out what the entropy is, because that's just going to be QH divided by some temperature, which you have to figure out, which you can just use your, what the temperature is, right? And you have the change in entropy of the big reservoir, right? Okay, so that is the outline. Okay, so I'm going to move on to the next one, okay? Problem 6. Which is, I guess, is the problem that most people have problem with.
Yes, sir.
Okay. All right, so I had to learn a bit of new physics for that. Well, actually, just had to think more than usual. So the problem 6 is giving you like two expansion process for two types of gases. The first one is for an ideal gas, and the second one is for a van der Waals gas. So let me first explain what the setup is. The setup is that you have a container, and and it doesn't say so, but you just assume when it doesn't say so that it's an insulated container. Then you have a gas and a piston. So this is the piston. So this is some initial state of this is I'm coloring the piston here, and the gas is over here. Okay, and here we have the initial volume of the gas is V, and the total volume is alpha V. Okay, so if I piston usually has this thing, and then what you have to do is that process 1 is that you slowly pull out the piston so that the gas fills up the whole volume of the container, and you pull it out by doing an isothermal expansion. So isothermal means that T remains constant, right? So that is A, process A. Process B is that you start with the same gas in the same initial volume, and temperature. And then what you do is that you just have some kind, and now let's just close the container like so. And we have some sort of barrier between the two. And this, and there's the gas here. And then what we do is that we suddenly remove the barrier. So when we suddenly remove the barrier, what happens is that, when you suddenly remove the barrier, the gas expands to the whole volume. It's a Joule expansion, right? So again, the whole barrier is, the whole volume is alpha times, alpha is some, positive number greater than 1. Okay, so these are the two processes that one has to consider. And in the first case, we consider this for an ideal gas, and we have to compute the change in entropy for both of these cases, okay? Now, the first one, in both cases, okay, sorry. So for the ideal gas, so anyone has any ideas how to go about it?
Use the first law of thermodynamics, assuming the internal energy doesn't change.
Right, but the first one, the internal energy does change, right?
T remains constant.
Yes, exactly.
But so it doesn't for an ideal gas.
For an ideal gas, it doesn't change. So for an ideal gas, we know that du is equal to Cv dt always. And because the first process is isothermal, that means that d of t is 0. And therefore, we know that, d of u is 0, right? And that gives us, from the first law, we get a relationship between TdS and P of dV, which is P of dV. And we know what P is for the ideal gas, so we can integrate this equation to find out the change in entropy. So that's easy. So that's, and for the second one, this is exactly like what we did in the Joule expansion, right? So what I would recommend is that you go back and look at the video on Joule expansion and or read the part in Blundell and then do the second problem, okay? I'm not going to say anything more about the second, about the B, okay? So the B would be, I'm just gonna say is that, this is the Joule expansion is, it's an irreversible expansion. Therefore, you cannot use this law to compute the change in entropy usually, because P is not well defined in the during this expansion. However, because entropy is a
state function.
Yeah, state function of state. Therefore, if you can calculate this final state somehow, then you have calculated from the initial state to the final state through a reversible process the change in entropy. Then you've calculated the change in entropy for the Joule expansion. And so that is the hint, and I will let you do the rest, okay? And let's look at the next one, which is the van der Waals. I feel like this is not how one pronounces this guy's name. He's probably some Dutch physicist whose name we are just butchering. Anyway, I'm sure we're not going to get sued. So the the van der Waals, who is a cousin of Rip Van Winkle, sorry about that, is gas is not an ideal gas. It's one of the realistic gases which arises from some sort of attractive intermolecular forces. So the equation of state is P plus n squared A is some constant, divided by, so A is a constant that depends on the gas, so we are not going to bother about that, some positive constant. So this is one, and then we have V minus V minus N of B, sorry, this is NB, where N is the number of moles, then we have nRT. Okay, so this is the equation of state for the van der Waals gas. So when we have this equation of state, it's good to solve this for P. So express this in terms of P. So when we get nRT by V by NB, yeah, so that minus n squared A by V squared, right? So this is going to be our expression for P. So for the first one, we cannot use the expression that the internal energy is not changing anymore. So what we should do is that we should use the fact that entropy is usually a function of E and V when we express in terms of the first law, this first law. But we can also think of entropy as a function of T and V, okay? Because these are also independent state variables. So if I do this, then the change in entropy is given by ds by dt, V remains constant, dt, plus ds by dv, t remains constant, dv. Okay? So for the first thing, dt, and why did I do this? Because I wanted to use the fact that dt is 0. Okay? If I use that fact, then the change in entropy is going to be given by ds by dv, where t remains constant, times dv. Now we use one of the Maxwell's relationships, which says that ds dv t is equal to dp by dt v. Now this is something you can compute from this expression for P. And game over. Okay? So for the second one, we basically use the same kind of argument, but see that in the second one, it's there is no guarantee that it's not an isothermal expansion, right? Because it's not an isothermal expansion, because it's not an isothermal expansion, this term is no longer going to be 0. Okay? So how do we deal with this? So we have to just convert this into something that involves P, right? So how do we do this? So remember that CV is dq by dt, where V remains constant, right? So then dq is T times ds. Okay, so ds by dt is, this is exactly what we have here. So we can replace this thing by CV times by T. So this term becomes CV times T. And then, we can just do this. Okay?
So we input the expression of ds by dt, constant v.
Yeah. This is very easily, you can integrate this very easily, right? And the second term you integrate it by using the fact that you know the expression for P. So this is how you find out, delta S for the Joule expansion. Now, one thing that they're asking you is that, what happens to the, what happens to the drop in temperature. So if I take the van der Waals gas and I do the second process where I remove the partition suddenly, then for the ideal gas, there is no change in temperature. But for the van der Waals gas, you can show that there is a drop in the temperature, okay? Now, so to show this, how should I explain this? One can use let me just get to the right part of my notes. Sorry. Yeah. So what happens is that, in the Joule expansion, the thing that remains constant is the internal energy, right? Because no heat goes out or into the system, and no work is done on the system. So U remains the same. So the thing that you want to compute is, now suppose there was a way of doing this in which and it doesn't matter how, and I actually don't know how it is done, that you remains constant, but you change the temperature slowly as you change the volume, okay? Suppose you could compute that. That thing has a particular name. It's called the Joule Coefficient, okay? Now, if I could calculate that, then the change in temperature would just be given by the integral of the Joule coefficient times dV from V to alpha V, right? But you're going to say, hang on, this is not the process that we are looking at when we are looking at the Joule expansion, because the Joule expansion, it's a sudden expansion, and therefore, all these nice, quantities such as temperature, pressure, a lot of the macroscopic, those things do not change continuously. They change discontinuously and in an irreversible way. So to take partial derivative of them is a travesty of calculus. And I would agree with you. However, if you were able to do this, By conservation of energy, you know that the final state that you're going to reach in state space will be the same thing as the final state that you reach by doing a Joule expansion, okay? And therefore, this is my argument. If you can calculate this, you're going to get the same change in temperature as in Joule expansion, okay?
So what's the derivation for this?
Derivation for this?
No, the temperature change in terms of the Joule coefficient.
I mean, this is the definition of the Joule coefficient.
Sir, I didn't get anything after hanging on.
After what?
After you said hang on.
Okay, I don't remember. Okay, let me reiterate what I was saying. Okay, so the idea is that we are looking at the Joule expansion of a van der Waals gas. Okay, so a van der Waals gas, the Joule expansion is an irreversible process, and therefore we shouldn't be able to use partial derivatives because these temperature, pressure, volume, these things are not well defined in the process of Joule expansion, right? I mean, they're well defined at the beginning, at the end, but not in the middle. So therefore, to calculate the temperature change using this formula for the Joule expansion doesn't seem correct at first. But I'm going to say it is because by energy conservation, the change in temperature, if you're able to do an expansion keeping U constant and T and V well defined through the process, it's going to give us the same end state as the Joule expansion. Okay, and therefore we can use the argument. These are functions of state to calculate delta T from this formula, even though delta, and that will coincide with the delta T for the Joule expansion. Okay?
So we are simulating the same environment elsewhere.
Exactly. We are using the same kind of argument that we use to calculate the change in entropy for an irreversible process. For the change of entropy for an irreversible process, we also had a similar argument that, we just have, because entropy is a function of state, if we can find some way of calculating the change in entropy, even though the process is reversible, it's going to be applicable for the irreversible process as well. Here we are doing the same thing, but instead for change of entropy, well, we also did it for change of entropy, but we are also doing that for the change of temperature, okay?
Yes, sir.
So I'm not going to derive how this leads to the answer because the derivation is very similar to what I've done over here for delta S, okay? So I want you to think about that. Okay, any more questions? So, okay, let me just somebody asked some questions here. So in the back channel chat, so let me get to that. And the question, let me read out. Sir, I had a problem on the entropy of mixing. I guess, okay, that's from previous, okay. So we found out that if either of the gases had the fraction of its atom compared to the total number of atoms as 0, as in X is 0 and X is 1, then the total entropy change is 0, yes. But isn't this the case of free expansion? The change in entropy in which is, no, in the free expansion, we actually change the volume of the gas. We double the volume of the gas. So there's more place in which the gas can go to. There's more space in configuration space, and therefore there are more arrangements, and therefore, and it's double, right? The number of the number of configuration has doubled, and that's why in the free expansion it changes by a factor of log 2. Okay, so that's in the second case. Isn't there work done on the gas while the pressure is constant? No. In the free expansion, which is the Joule expansion, there is no work being done by the gas or on the gas, because the gas is not pushing on any piston and nothing is pushing on the gas except itself. So the gas as an entity is not doing any work, or it's being worked upon. Okay, I hope that answers your question. Okay, I think Nian, you sent me some questions on Slack. Did you want to discuss that? Sorry, I haven't been able to answer them on Slack, but I can discuss them here if you want.
So, ek minute, আমি just two questions দেখে নি আবার।
Yeah, you had something about like being an equivalence class or something.
হ্যাঁ, আমি হচ্ছে যে লাইক স্টেট স্পেসে যদি একটা পয়েন্ট থেকে আরেকটা পয়েন্টে রিভার্সিবলি যাওয়া যায়, আর ওই পয়েন্ট থেকে আরেকটা পয়েন্টেও যদি রিভার্সিবলি যাওয়া যায়, তার মানে হচ্ছে আমরা ফার্স্ট পয়েন্ট থেকে লাস্ট পয়েন্টেও একটা রিভার্সিবল পাথ পেয়ে গেছি, তাই না?
Right, exactly. Yeah, so it is kind of a equivalence relationship.
হ্যাঁ, সো যদি এরকম হয় যে আমরা পুরো স্টেট স্পেসটাকে একটা পার্টিশন করতে পারি, যে প্রত্যেকটা পার্টিশনের সবগুলো পয়েন্ট হচ্ছে একটা থেকে আরেকটার হচ্ছে রিভার্সিবলি ইয়ে করা যায়, লাইক তো এটা কি একটা গ্রুপ পাওয়া যায় কিনা, যে মানে পুরা ইয়েটাকে একটা গ্রুপে ইয়ে করে ফেলা গেছে?
Right, you're saying if it can be given the structure of a group, right? Yeah, I mean, like equivalence.
But problem হচ্ছে যে তখন আইডেন্টিটি এলিমেন্ট কি হবে, মানে কোনো একটা পয়েন্টকে হচ্ছে আমরা ধরতে হবে যে যেটা সব পার্টিশনেই থাকতেছে।
No, you don't.
We don't have elements in common in partitions.
হ্যাঁ, এটাই তো। তো মানে এটা একটা ইয়ে হয়ে গেল যে একটা পয়েন্ট সবগুলোতেই থাকতে হবে, মানে ওই পয়েন্ট থেকে সবগুলো পয়েন্টই হচ্ছে।
But why do you want to form a group out of a partition? Like, it doesn't really match with the structure of group in many ways, right?
Well, partition বলাটা তাহলে ঠিক নেই, মানে জাস্ট একটা কি বলা যায়, কয়েকটা সাবসেটে ভাগ করার, যেটার একটা পয়েন্ট সবগুলোতে কমন থাকবে এরকম একটা স্ট্রাকচার।
Right. So I mean, I think there is a mathematical structure similar to that. It's called a holonomic group. Okay. Do you know? Have you heard of holonomic groups?
I've heard, but I don't know what it is.
So what the holonomic group is that it's slightly, well, I mean, no, sorry. I think holonomic group at Aro basic, there's a something called a homotopic group. Homotopic group is more, it's a basically
homology,
sorry, not homology.
Cohomology একটা subject বা
yeah, cohomology is different. Yeah, cohomology is the dual of homology. That's why it's called cohomology. So let me just like Nian give you a very short, because it just goes outside the scope of this lecture. Homotopic group is, suppose you have a space which has a hole in it. Okay. So this actually space can be given some kind of a group structure. And the group structure would be there are two types of elements, two types of loops in this space. Loops which can be shrunk into a point, and loops that cannot be shrunk into a point. Okay? And what you can show is that, you know, you can associate with loops that can be shrunk to a point to the identity 1, to the element 1, and loops that cannot be shrunk to a point, so the loops that go around the whole, you can associate with -1. And then composition of two loops can be that they join at a point. So you go around 1 like this, and then you go around 1. Then if 1 times 1 will give you 1. So that is the multiplication, okay? And if you have one loop like this, another loop which goes around the whole, and they have a common point, then you're multiplying 1 with -1, and then you get a -1. And you can show that by making a cut here, which you define as, you know, like this. You can turn this loop into one loop, but that one loop now goes around. So this goes like this, so that one, this goes like this. That one loop goes around the whole. And therefore, it is proven that this multiplication leads to this thing, right? So homotopy, that is just one example. It can, depending on the space, the homotopic group can be very, very complicated. Okay, so this is an example of a homotopic group, which is a Z2 group. Okay, so I think you're thinking along those lines. So yeah, I mean, it is a little bit outside the scope of this course, but you know, I hope that at least starts you with. So we can have a conversation about this a little bit offline, because I think, you know, but I hope, you know, that helps you a little bit. Yeah. Okay.
Yes, sir.
But yeah, it's an interesting idea, but we can talk about this more later. Anybody else who has questions from the assignment?
Can we?
I had just a short question. In number 6, it never says that we have to calculate the entropy of the case B. So are we supposed? It says repeat this calculation for case A, assuming that the gas obeys van der Waals.
Oh yeah, you're right. Yeah, you're right. So, by the way, number 6, I think I'm thinking of increasing the point from 10 to 15. Okay, because it's a much harder problem. So you're right.
Now,
sorry, Saif, you're right. You just have to calculate, but you know, it's very similar to calculating delta S.
আমরা কি যে ভ্যান ডার ওয়ালস ইন্টারনাল এনার্জির কোন একটা এক্সপ্রেশন বের করে এরপর তো ক্যালকুলেশন ইজি হয়ে যাবে।
The thing is that, you know, to understand the cooling, you basically what is happening in the van der Waals expansion is that, you know, its potential energy looks something like this. So when the gas expands, what happens is that, you know, the potential energy actually increases, right? And therefore the kinetic energy decreases. Potentially increases because there's more space between the gas molecules, and the kinetic energy decreases as a result, because total energy is preserved, and therefore it leads to a cooling. Whereas, you know, for an ideal gas, there is no potential energy, right? So therefore there is no cooling there.
U includes potential and kinetic, right?
Yeah, exactly. Sorry, so it should not be U. It should be V. Yeah, it's confusing because a lot of times, you know, in a lot of branches in physics, U is used for potential energy, right? So, but V, I should use V. You're right.
Sir,
Any more questions? Yeah.
I had a question, but it's outside the assignment, but inside the course.
Yeah, why did you ask it?
Uh, I sent it in the chat.
Okay, I see. Okay, good.
I didn't get the second graph, and the connection to the first graph is probably from lecture.
Okay, you went, there are like several chats here, so you have to specify which chat it is. Oh, in the, okay. Sir, I didn't get the second graph in 826. Okay, let me see.
Sir, 8:26 was the time I copied from the Slack. You can check our DM in the chat.
Yeah, I am looking at that, yes. But it's asking me to sign into Slack. Can you just send me the picture somewhere on... Can you say...
So I
like,
can share the screen.
Yeah, yeah. Let me just like, let me unshare the screen so you can share the screen, okay? I don't think I have to unshare, but anyway, stop sharing. All right. Yeah. Okay, yeah. Farhan, you're muted, so we can't hear you.
Oh, sorry, sir. I didn't understand the second graph and its connection to the first graph.
Oh, I see. Okay, so the second graph is the heat capacity as a function of temperature. So that means that it's telling you how easy it is for the system to absorb energy as you change the temperature. Now we see that, you know, when the entropy is about half the possible highest value it can get, the temperature is infinite, right? Because
Yes,
the rate of S with respect to that becomes zero, right? With energy. Because the x-axis in the first graph is energy. So that means that as you increase temperature, it gets harder and harder to impart energy into the system. You get less and less efficient.
Sir, in the first graph, where is the t-axis? I didn't get how the temperature is going to defined.
Yeah, the
here.
x-axis is E, energy.
Oh, so E is the equivalent of temperature here.
No, energy. So temperature is 1 over T equal to, what is it? Del S by del E.
Oh, I get it now.
Yeah, so because the slope at the middle goes to 0, the temperature goes to infinity in the middle. So in the lower graph, it's really when T goes to infinity on the very right that you reach the middle, you reach half the possible amount of entropy. So it's really the entropy, the increase in entropy, because usually what you have is that, you know, if you have more and more temperature, you're giving the system a lot of, you know, like photons or, you know. So in principle, it should be able to, the system should be able to, you know, jump to a higher energy state very, very quickly. So its heat capacity should naively be very high. But what is happening here is that the number of states that you can jump to is so large because the entropy is increasing, and, you know, the number of system is the exponential of the entropy. So, you know, so the number of system is increasing very, very rapidly. So that's why, you know, you have, you know, the efficiency by which you are, you know, you're getting into those states is much, much lowered. Here, efficiency is used in a very loose term.
Oh, okay, sir, I got it. Thank you.
So entropy dominates high temperature. Okay, anyone else has any questions? Okay, if not, thank you very much, and we can. So, can you give the assignment by end of Friday, please? I will make sure that the link is live.
Okay, sir.
Yeah.
Okay, thank you very much. It was fun solving problems together, and I'll post another assignment soon. Okay.
Okay,
Thank
sir.
you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Can Afia, can you stay behind for a minute?
Yes, sir. Here.
Sir, is it possible to get problem solving from lectures with Wasif sir?
Yeah, I did this because Wasim is very busy right now. Because he's also a PhD student in California, so he has some exams. That's why I was like, I did this. Okay.
Oh, sir, I had some questions from lecture 5, 6, 7, 8, 9, 10, and 11. Just
Okay,
small questions.
so maybe you and I can make another appointment, and I can discuss one-to-one.
Okay, then.
Okay.
Thank you, sir.
Okay.
Goodbye.
Okay. Bye. হ্যাঁ আফিয়া কি খবর তোমার?
Sir,
Okay,
asking,
let's
sir.
stop. And let me make sure this is being recorded. So let me just, okay, can we just like, yeah, sorry, this, I don't want to record this, of course. So just hang on, okay? Just let me stop recording this. Okay. Okay, yeah.